Hello everyone, this is Professor Keen. In the past few lectures, I've been talking about Newton's first, second, and third laws of motion. I left off talking about Newton's third law of motion. That is, to every action, there is an equal and opposite reaction. I used Newton's example of if your finger pushes on a stone, then the stone pushes back on your finger. And this is a typical characteristic of any instance of Newton's third law. You have two interacting objects, and one object pushes on the other, and the other pushes back on the one. So let's do another example. As I always say, this law is probably the easiest to state, but the most perplexing to actually figure out. So let's do another example. Newton's third law of motion. Okay, so I want you to consider a specific situation. Okay, let's suppose that you are driving in your little Volkswagen Bug. Okay, so here's your Volkswagen Bug. It's your VW. Okay, and you are driving along, and I'm going to draw an arrow here represent the velocity of your car. Okay, that's the velocity of the car. And so you're going along the road. And let's suppose you have the unfortunate, God forbid, scenario of having an enormous semi-truck approaching you at high speed. So here we go. Okay, here is a semi-truck that is approaching you at some high rate of speed. All right, and I'll draw the velocity of the semi. Okay, so here we go. And I want you to consider a head-on collision between the Volkswagen Bug and this semi. And I'm going to ask you a question. So here's my question. Which feels the greater force during the unfortunate collision? Okay, so of course before they hit there's no force of interaction between the two, but at the moment they're colliding, which one feels the greater force? Is it the Volkswagen Bug that feels the greater force? Is it the semi that feels the greater force? Or is there another option? And typically students have a sense that when you first see this problem, your immediate reaction, I don't know if it's your immediate reaction, but many people's immediate reaction is that, of course, the Volkswagen Bug feels the greater force. So the assumption that many make, which sounds kind of reasonable, right, is that the car feels the greater force. But I'm going to argue that this is not correct. This is not correct. And why is it not correct? Well, if we take Newton's third law of motion seriously, for every force there is an equal and opposite force, it implies that the force that the Volkswagen Bug feels is exactly equal to the force that the semi feels. That is, the semi pushes on the Volkswagen exactly as hard as the Volkswagen pushes on the semi. So by Newton's third law, the force acting on the car is exactly equal to the force acting on the semi during the collision. Okay, so when we say for every force there's an equal and opposite force, that's the implication, that the force acting on the car, maybe I'll write this as force acting on the car is equal to the force acting on the semi. This is precisely what Newton's third law is stating. So it's kind of a counterintuitive sort of law. Okay, it's easy to say for every action there's an equal and opposite reaction, but it's a little bit harder to believe. Your intuition perhaps tells you, no, that doesn't sound right. Now here's the reason why it is in fact correct. Many times our notion of force is confused with our sense of acceleration. Okay, so let me write it in this way. So this is Newton's third law. That's the claim of Newton's third law. Let's insert Newton's second law. And I'm going to insert Newton's second law in the F equals ma format. So the force acting on the car is equal to the mass of the car times the acceleration of the car, right? So I'm basically substituting in Newton's second law. And the force acting on the semi is equal to the mass of the semi times the acceleration of the semi. So I'm inserting, this is by Newton's second law. In other words, whatever force is acting on the car is causing the mass of the car to accelerate it this much. And whatever force is acting on the semi is causing the mass of the semi to accelerate by this much. Okay, so we're taking Newton's third law seriously and Newton's second law seriously. Okay, now what I'm going to do is I'm going to rearrange these a little bit. So acceleration of the car is equal to, I'm going to divide both sides by the mass of the car, the mass of the semi divided by the mass of the car times the acceleration of the semi. And here you might see where I'm going with this. Which body, which mass experiences the greater acceleration? Well, the mass of the semi, the numerator of this formula, this numerator is huge because the mass of the semi is very big compared to the mass of the car. In other words, this quantity is much, much bigger than 1 because the mass of the semi is enormous compared to the mass of the car. So if the semi experiences some acceleration, you multiply it by a very large number, the car is going to experience a much bigger acceleration. In other words, the acceleration of the car is much, much bigger than the acceleration of the semi. And this is the resolution of this seeming paradox. When you have a car being struck by a semi, it is certainly true that the car, which is initially going forward, suddenly experiences an enormous acceleration. Perhaps it slows down, perhaps it stops, perhaps it's even thrown back in the other direction. The acceleration is enormous. On the other hand, the semi, because it's originally going forward, it experiences a relatively small acceleration. Perhaps it slows down by just a little bit, but keeps going in the same direction. So this is the source of many people's confusion. They confuse the acceleration that something feels with the force that it feels. What we're saying here is although both objects, the car and the semi, feel the exact same force, they respond to that force very differently. That is, the car experiences an enormous acceleration, whereas the semi experiences a relatively small acceleration. So we can hold to our common sense intuition about the response of things to force and still hold to Newton's third law and Newton's second law of motion. So there you have it. There's a short introduction to an application of Newton's third law. Let's do one other application of Newton's third law before we end. Okay, so let's think about a collision of two objects. This is going to be relevant when we do our next lab experiment. So let's suppose we have a mass that is moving in this direction with a certain velocity so that the momentum, I'll write this as the momentum of object A. So this is object A, that's the momentum of object A. And object B, let's say this is a small object, and its momentum is in this direction. Okay, so this is example 2. This was example 1. Okay, so what happens? When they're flying toward each other, at some moment, they are going to collide with one another. Okay, so here's the collision. And at the moment of the collision, ball A is going to push on ball B, and ball B is going to push on ball A. And so I'm just going to draw the forces right here. And again, by Newton's third law, the force acting on ball A is exactly equal to the force acting on ball B. They're simply directed to contrary parts, as Newton would say, or in opposite directions. So they both feel the same force, but the forces are exhibited in opposite directions. Okay, so in other words, force A is equal in size to force B. This is Newton's third law, right? And now we can write, using Newton's second law, what is the force on A? I'm going to now write it as mass times acceleration. Well, I'm not going to write it as mass times acceleration. I'm going to write it as the rate of change of momentum of ball A and the rate of change of momentum of ball B. Okay, so while they're in contact for some very tiny time interval delta t, they both suffer a change in their momentum. And of course, the time that they're in contact, the time during which force A is applied to ball A and force B is applied to ball B, are the same time intervals, delta t. So these are the same on both sides. So I'm going to cancel these out and just write the change in momentum of ball A is equal to the change in momentum of ball B. Okay, so let me go back. This is Newton's second law that I'm inserting here to exchange forces with rates of change in momentum. And there I'm canceling out my delta t's to get down to here. Now, this is an important observation, which we're going to talk more about in the next chapter, but I'm just giving you a heads up about it here. Newton's laws of motion imply what is called the conservation of momentum. What the conservation of momentum is going to tell us is that when you have a system of interacting objects, in this case it is two interacting balls, there are no external forces acting on this system. We're assuming that they're just sort of flying through space, so there's no external force acting on them. The only force are forces of interaction between the two objects. In that case, when there are no external forces acting on the system, the total momentum of this system of objects remains constant. How is that illustrated by my derivation here? Well, this object was originally moving with a momentum PA, this one with momentum PB, and what this is telling us right here is that whatever momentum is lost by ball A is precisely equal to the momentum gained by ball B. Or conversely, whatever momentum is gained by ball A is lost by ball B. So there's kind of a balancing going on here. Although one ball or the other ball might slow down or speed up, and so its momentum changes, the other ball's momentum change exactly compensates for this, so that the total momentum of this system is conserved. We're going to talk more about this in the next unit, but I thought I would mention how this follows from Newton's laws of motion right away. Okay, and I'll stop there.